Okay, now it's being recorded.
Okay, so let me start. I will turn off my camera right now because I think it reduces the size of the final. Okay. So today I will talk about my very recent work on convergence of eigenstate expectation values with system size. And before presenting the rigorous aspect of this work, I try to first show you some numerical results in order that you have some feeling of the problem that we are going to study today. Now we consider a particular spin chain Hamiltonian. The Hamiltonian is written in the bottom here, and we have L is the system size, and it is a spin 1/2 and sigma are the Pauli matrices. And we have a particular Hamiltonian. These coefficients here are generic numbers. And for this particular Hamiltonian with periodic boundary condition, we can just compute all its eigenvectors and eigenvalues. The eigenvectors are labeled by n, and its energy, the eigenvalue, corresponding eigenvalue is E sub n. And we do this plot. The horizontal axis is the energy density, that is the energy of a particular eigenstate divided by the system size L. And the vertical axis is the expectation value of a particular operator. Here I choose it to be sigma 1x. But clearly, because we have a translation invariant system, it doesn't depend on where the operator is. And we can draw this particular particular figure. And we consider 3 different system sizes. L is 15, 17, and 19. And for each particular system size, we just have some dots or some crosses plotted on this figure. Unfortunately, this figure is black and white, so that it's not very clear, but you can still see from the darkness of the symbols. The darker, the larger system size. You see that for L is 15, from L is 15 to L is 19, you see that the fluctuation of this fluctuation of the data is kind of reducing. And you see that as the system size goes larger, it kind of, it seems that it converges to a smooth function of energy density. So this is a phenomenon that we are going to study today. The question we are going to study here is that how fast eigenstate expectation values, EEV stands for eigenstate expectation value of a local operator, converge to a smooth function of energy density as system size diverges. The main results of this work is the following. If we consider transition invariant quantum lattice systems in any spatial dimension, we can prove that for all but measure zero set of local operators, the deviations of finite size eigenstate expectation values from the aforementioned smooth function are lower bounded by 1 over big O of n, where n is the system size. That is, we try to establish a lower bound on the convergence of finite size eigenstate expectation values to the smooth function. And we can show that we cannot show this bound for all operators, but for most operators, in the sense that the exception consists of measure zero sets, we can have a lower bound. And in particular, I would like to emphasize that this lower bound holds regardless of the integrability or chaoticity of the model. The only assumption here is the translation invariance. And furthermore, if we consider a specific, more specific type of systems, that is not only translation invariant, but that the systems satisfy the so-called eigenstate thermalization hypothesis, we can prove this is a lower bound, and we can prove a matching upper bound, so that the upper bound just matches the lower bound up to a prefactor that is hidden in the asymptotic notation, in the big O notation. This is a very brief summary of the results. But here, in order to present the results more precisely, I need to define I need to show how to define the deviations. Everything needs to be defined rigorously later in this talk. Before considering any rigorous result, let me first give a very brief overview of asymptotic notations. These notations are very standard in computer science or in calculus, but it seems that some physicists use a different system, so that I think it is better to introduce them here in order to avoid any confusion. We have some notations that will be used in later in this talk and also in the paper, big O notation, big omega notation, big theta notation, little o and little omega. Big O means that as x goes to infinity, then f is bounded above by g up to a constant. So that little o doesn't require that f and g are in the same order. F can be much less than g as x goes to infinity. And the big omega notation means the other way. That is, f is bounded below by g asymptotically. And the big theta means that bounded both above and below by g. And we can also have little o and little omega. Little o means that f over g goes to 0 as x goes to infinity. And omega means the opposite, that is f over g goes to infinity. So I noticed that sometimes physicists use a different system in the sense that when they write down f is O, big O of g, they really mean that f is big theta of g. And they do not use other notations. So that I just give a brief introduction of these notations here. To present the results, let me first give a presentation of the setting that we consider. First, we present our results in one dimension, but this is only for simplicity. And it is easy to see that the same results with the same proof goes to higher spatial dimensions without any essentially new ideas. So that we only consider one dimension. And in this case, we have a spin chain, and suppose that d local is a local dimension of each spin, and it is a constant. Then the total dimension of the Hilbert space is exponential in d local. For instance, you can imagine that d local is 2, that is, we consider qubits. And the T is the lattice translation operator. That is, we have a lattice system and we translate by one lattice site. And it is defined as the following. If we have a computational basis state, then T acting on this state just brings the last state to the first. And because we have periodic boundary condition, there is no boundary. And with the translation operator, we can define a series of local Hamiltonian. The way we do that is that we first pick up particular local term. Here we call this local term as a little h, and we suppose that little h is acting on the first k spins. And then using the translation operator, we can move the little h term to translate it to other parts of the lattice, so that if the lattice, if the number of spins is a capital N, then we have a Hamiltonian like this. And we may assume without loss of generality that the trace of h is 0, because we can just shift h by a constant multiplied by identity. So that we can assume without loss of generality that little h is traceless, so that the capital H, that is a Hamiltonian, also traceless. And the operator norm of little h is 1. Now come to the rigorous definition of the convergence speed of eigenstate expectation values. First, we let J to be a complete set of translation invariant. Ti stands for translation invariant eigenstates of H, with the corresponding energies E sub J. The total number of J here is just the dimension of the Hilbert space. And with this, we can try to define the convergence, that is the distance of finite size eigenstate expectation value to the smooth function. But one technical issue here is that we don't know what is this smooth function is. So that in order to avoid this technical difficulty, we choose the following strategy. That is, we first think of an arbitrary smooth function. We call it f, and we can define the distance to of finite size eigenstate expectation values to f. And then for each f, we have a distance, and the distance depends on system size n. So that we, from all such f, we then choose the optimal f. The optimal f is defined as the f such that the difference decays fastest as n goes to infinity. So this is a strategy, and let me come to the more details about this definition. First, we have a traceless local operator A, and we assume that A is of unit operator norm. And then we can consider a particular function f. F is arbitrary, and the f must be n-independent, because we should imagine that the optimal f corresponds to the smooth function of energy in the thermodynamic limit. So the f should be n-independent. And then we can define little r f n as the following. So this term is just the eigenstate expectation value minus f of ej over n. Ej is the energy of eigenstate j. Over n means that we consider the energy density. And then this is a difference. We just compute, for each j we have a difference, and we just compute the RMS value of all the numbers for each j. This is defined as a little rf. And this definition it doesn't guarantee that little rf decays monotonically with n, so that it is not very nice in this sense. And in order to have this nice property, we can define related quantity called capital RF, which is just defined as this. This definition is good in the sense that capital RF is by definition monotonically non-increasing, and it is trivially upper bound of little rf. And we assume that f is smooth, and in particular, we require that f has a Taylor expansion around x is 0 to the second order. And up to this stage, we define little r and capital R for every f, and then we need to define the optimal f. The optimal f in this talk, it will always be denoted by a hat. So the optimal f is defined as the f such that the finite size error, capital R, decays the fastest as n goes to infinity. So that if there exists an optimal f, it must obey this particular equation. That is, for the optimal f, it is a capital O of, it is a big O of any other f. And the optimal f just gives the convergence speed or convergence rate of the eigenstate expectation values of A in the thermodynamic limits. So notation-wise, I should emphasize that the little rf or capital RF, these are the finite size error. And the optimal f, if it exists, it's of course depend on the local operator under consideration. And in this sense, should carry A as a subscript. But for notational simplicity, I have omitted A in these notations. So after this definition, let us gain some intuition or gain some feeling about it by considering a particular example. which is a trivial example, but it still is useful for our results, for understanding our results. In this particular example, we consider the case that the local operator is a little h. Recall that little h is a term in the Hamiltonian. And in this case, imagine that our problem is to understand how the eigenstate expectation values behaves as a function of energy density. If A is chosen to be h, then the eigenstate expectation value of A is just the energy density. So that in this case, trivially, energy density is itself. So that we have an optimal f, which is just given by fx is x. So that fx is the argument itself. And in this case, we have the error capital RF is 0 for any n, which just says that the energy density is exactly the energy density. And in this case, we see that for any transition invariant local Hamiltonian, we can choose a particular local operator, just the term of the just one term in the Hamiltonian, so that the finite size error can be exactly 0, which means that it is not possible to prove any non-trivial lower bounds for all local operators. So that the main result of this talk is to show that if we do not consider all local operators, but almost all local operators, we can prove a non-trivial lower bound. But before considering lower bound, let me first present an upper bound. The upper bound is indeed very straightforward, is an immediate consequence of the so-called weak ETH. So weak ETH is one statement of weak ETH is just given by the lemma I presented here. It says that if we consider traceless local operator A, and suppose that its norm, operator norm is bounded, then we have this particular equation. Here, J is just the eigenstate. We compute the eigenstate expected value and take the square average over all eigenvalues. We have it is of order 1 over n. So this can be proved for any transition invariant system. So that weak ETH, even if it ends like, even if the terminology ends like weak eigenstate summarization hypothesis, it is not a hypothesis, it's just a theorem. And if we start from weak ETH immediately, what we see is that if you compare the definition, we must minus something, and we can just take this to be 0. Then we have the eigenstate expectation value square. So that here you can compare, we directly have eigenstate expectation value square. The way we do is that we just choose f is exactly 0. In this case, compare it with our definition, the difference is a square root, so that we have a square root. That is, in any transition invariant system, if we choose fx is 0, then we have an upper bound. And if an optimal f exists, then the upper bound just translates to the optimal f. So we have an upper bound for any transition invariant system, which is 1 over square root of n. And this slide shows the proof of weak ETH. It is a very straightforward proof. It is a one slide proof. I will not go through the proof here because I wish to save time for the conceptual part of this talk. But here, this slide just means that it is very easy to understand it. It's just a few minutes for you to understand it if you are interested in the proof. It makes non-trivial use of the transition invariance. If we do not have transition invariance, then of course weak ETH, the statement here doesn't hold.
Sorry, I think I just missed something. So how, the terms of the Hamiltonian could be traceless. So why does this not apply to them? Or what am I missing here?
So I don't understand your question. That is.
So I thought for the terms of the Hamiltonian, they converge to the function f of x equals x. But now you're saying for traceless terms, they converge to f of x equals 0. So why is there not some tension there?
Here I do not say that it converges to fx equal to 0. I just say that if you that is if you plug in fx is 0, you get it decays to 0. But this doesn't really mean that it converges, in the sense that if you look at this definition, it is in some sense it is average over all eigenstates. So that even if in this definition, let's say little r f goes to 0, it doesn't mean that doesn't mean that for every eigenstate it converges. It just means that let's say most eigenstates.
Good. So I guess in general, I mean, so this is maybe a common situation where there are multiple f's that give rise to capital R sub f decreasing with n.
Yeah, it could be. That is this definition doesn't guarantee that the proof is pointwise. The convergence is pointwise.
Right, just sort of average.
Yeah.
So
yeah, it could be that some particular eigenstate, an exponential number of eigenstates, it doesn't converge as long as the fraction is small.
So just to clarify then, for little h, it works for f equals 0, for both f equals 0 and f equals x, you have capital R sub f decreasing. So yeah, maybe this is a general situation that there are many very kind of different looking values of f that.
Yeah.
Okay, all right, thanks.
Decreasing with different speed with respect to it, yeah. So let me try to come to the lower bound, that is the main results of this talk. And I try to give some intuition, but I will not show the full proof. In order to give some high level sketch and intuition, I need to start with some ingredients that will be useful for us. The ingredient here is about the spectrum. It is generally true that if we have a many-body system with local Hamiltonian, then the density of states approach normal distribution in the thermodynamic limits. So intuitively, you might start by imagining that if you have a Hamiltonian and each term is only an on-side term, there is no interaction, then it is trivially, the density of states trivially approaches the Gaussian distribution. But the statement here is that even if you have, let's say, nearest neighbor interactions, this remains to be true. And you can compute the variance and the standard deviation. You see that the standard deviation should be square root of n. So that if you consider eigenvalues of the Hamiltonian, then for almost all j, we have that E sub j is of the order of square root of n. And from the density of states, you can also see the tail of the Gaussian distribution. That is, if you have a lambda which is slightly larger than square root of n, let's say here it is some constant times the square root of n times log n inside the square root. Then you can see the fraction of eigenstates with energy greater than lambda, energy magnitude greater than lambda. The fraction is inverse polynomial in system size. This just follows from the Gaussian distribution with standard deviation square root of n. And with this in mind, we can have some calculation. And I will not go through this calculation line by line, but roughly speaking, I will just go through it at a high level. So the notation here is that if x is equal to y with the delta above the equation equal sign, which means that x is approximately y up to additive error delta. and we choose the energy cutoff as mentioned in the previous slide, so that we can have some calculation. The left-hand side, the left side is 0, and we do something like this. In this calculation, we use the sum of, so for instance, this step is just the definition. That is because the difference between the eigenstate expectation value with respect to the smooth function in our mind is quantified by little r. And then we can only consider the middle of the spectrum because it is a Gaussian distribution. And the middle of the spectrum, the difference, the error introduced in this step is given by the fraction of eigenstates that is away from the middle of the spectrum. So that if energy cutoff is lambda, we have an inverse polynomial. And then we can do some Taylor expansion. We have assumed that F allows Taylor expansion. And then eventually what we get is that 0 is equal to F of 0 plus the second derivative of F times trace of Hamiltonian times little h over 2 and d. D is the dimension of Hilbert space. So that trace of capital H little h over d is a constant that doesn't depend on n. So this calculation applies to every f. So that if we consider a particular f such that the little r f goes to 0 as n goes to infinity, that is a little o of 1 for a particular f, then first we observe that f0 is 0. This is because if we look at each approximation step, the error just goes to 0 as n goes to infinity, because Q here is the inverse polynomial in systems in n. And lambda cube over n cube, lambda is roughly up to logarithmic correction, it is square root of n, so that it also goes to infinity. So everything goes to infinity and goes to 0. And the second term also goes to 0 because we have an n in the denominator, so that f0 is 0. And furthermore, if we plug in f0 is 0, we compare the error terms, approximation error terms, then we have the following inequality, which says the following. The little rf, that is a finite size difference, is upper bounded by the first term minus order of q. Q is the inverse polynomial of arbitrarily high degree minus all big O of gamma lambda cube over n cube. So that you can see that Q is an inverse polynomial in n, which is an arbitrarily high order polynomial. So that this is very small. Lambda cube over n cube, lambda is roughly square root of n. So this is roughly n to minus 1.5, but the first term is 1 over n. 1 over n because we have an n here. Assuming that the second derivative of f is non-zero. So this gives you some intuition regarding to a 1 over n lower bound, because if you choose f to be the optimal f, and the optimal f is just the smooth function in the convergence too, and you might expect that the optimal f doesn't have the property that the second derivative of optimal f is 0. Then you just get a lower bound, which is a 1 over n. But in order to make this statement precise, there is some additional amount of work, involves some longer calculations than the one I presented here. So that eventually what you get is the following. So from the previous slide to this slide, I skip some calculations so that the lemma in this slide might not be very obvious to you why it holds, but it is kind of related to the calculation in the previous slide. So eventually what we have is that if you start by considering a particular traceless local operator with operator unit operator norm, and if there exists a smooth function f and exists a strictly increasing infinite sequence ni, so that little r f is little o of 1 over n for n in this sequence, then what you get is this particular equation. So this particular equation just follows from the one in the previous slide. That is, if you have a little rf is a little o of 1 over n, what you get is that little o of 1 over n is greater than or equal to this, which means that the second derivative of f is 0. The second derivative of f is 0 combined with little r f n is a little of 1 over n. Combine them together after some calculation, you can get this particular equation. I need to mention that this particular equation here, because n is a variable, so that strictly speaking, we have one equation for each n, but whether this equation holds or not doesn't depend on n, because both sides of this equation are independent constants. To see this, you can see that if we consider a particular factor in this equation, let's say this vector, 1 over d times trace of h a, we have assumed that both h and a are traceless, the terms in h and a traceless. And if you try to expand h in its local terms, what you get is that you have a summation, and you require, the restriction here is that the local term in h, the support of local term in h and support of a must, there must be some overlap. Then you can see that the summation is done over a neighborhood of the support of a, so that it doesn't depend on system size. The same argument applies to other terms in this equation. So that this equation, whether it's valid or not, is independent of n. But if you look at this equation, you will see that there is no reason to expect that it holds for most local operator a. So then what you need to show next is to show that the set of traceless local operators that satisfy this particular equation has measure 0. If you can show that, then you are done with the result. And in order to show that, we further observe that both sides of this equation is a linear function of a. Therefore, if you consider the solution of a linear equation, then either the linear equation is just 0 equal to 0, which means that every a is a solution. Otherwise, what you'll see is that the solution is a lower dimensional manifold. Lower dimensional manifolds has measure 0. So the final task here is to find a particular a such that this equation doesn't hold, and it is possible to do that for any little h, that is for any local Hamiltonian. And combine all I said together, eventually we get a theorem which gives you a lower bound on the finding size error. It says the following: if we define a local traceless local operator a as rapidly converging, we define a as rapidly converging if there exists a smooth function which depends on a such that this lower bound doesn't hold. If the lower bound doesn't hold, we call it rapidly converging. Then we have shown that the set of rapidly converging traceless local operators has measure 0. This is the main result of this talk. Now let me try to comment on the relationship between eigenstate thermalization and hypothesis. So previously I mentioned the weak ETH, but when we talk about ETH in the literature in the community, if we do not say weak ETH, what we usually mean is a strong ETH. So strong ETH is expected to hold in non-integral models where energy is the only local conserver energy. But the strong ETH is really a hypothesis. And the ETH just says that, just gives you on that for the matrix elements of a local operator in the energy eigenbasis. And it says both about the off-diagonal and also the diagonal matrix elements. For our purpose, we only look at the diagonal part. The diagonal part says the following. So if you have a local operator A and its diagonal matrix element is given by G of Ej over n. Ej over n is just the energy density. G here is a smooth function of its argument, plus some fluctuation term. The fluctuation is given by the exponential in minus S. S is the thermodynamic entropy. That is a log of the density of states at a particular energy Ej over 2 times delta J. Delta J is just upper bounded by a constant, and it varies irregularly with J. So that from this particular ansatz, you might think that A, that is eigenstate expectation value, just converge to G. And then if you choose F to be G, then the error R sub G n goes as exponential in the system size, because the energy, the thermodynamic entropy is extensive. Extensive means that it's proportional to n. So that it seems that it contradicts our theorem previously proved, because we have a lower bound which is 1 over n. But this argument is problematic because here G may depend on n. That is, in the statement of ETH, it is a statement for each n. It doesn't really say the relationship between n and n plus 1. So that in this case, G should, in this ansatz, G really depends on n, and G should carry n as a subscript. In this case, our theorem it turns out that our theorem says that G sub n cannot converge too fast in the thermodynamic limits, because the fluctuation term is exponentially small in system size, so that it can be neglected. And then our theorem just says that G of n, if it converges, then it doesn't converge faster than 1 over n. And furthermore, previously we have an upper bound, which says that capital R is upper bounded by 1 over square root of n. That is a consequence of weak ETH. Now we formally have a strong version of ETH. It is interesting to see whether we can improve the upper bound. The answer is yes. The answer is yes. So that we can improve the upper bound. But before giving you the improved result, let me first define ETH more precisely. That is, our assumption here is that ETH assumption is that it suffices to assume that it holds in the middle of spectrum, because as I mentioned, most eigenstates have energy in the middle of spectrum. So that we have an assumption, and here in the middle of spectrum is handled by a particular small number epsilon. So that we only require that this particular inequality holds for all j, such that Ej is less than or equal to n times epsilon for an arbitrarily small constant epsilon. And in this energy interval, we require that the eigenstate expectation value is close to a particular smooth function. This smooth function can depend on, that is, in fact, we have a series of smooth functions, one for each system size n, so that the error is upper bounded 1 over inverse polynomial in n. I need to mention that the ETH ansatz previously mentioned in the previous slide, the error is a fluctuation term, which is exponentially small in n. But here, because we are taking an assumption, it is sufficient for our purpose to assume a weaker upper bound. It is sufficient for us to get the result. So that I just consider a weaker inequality here. So that this assumption doesn't really say any relationship between Gn and Gn plus 1. So it's, in principle, it could be very different. But in practice, if we have this assumption, then we can show that we can find a particular f such that the finite size error is bigger of 1 over n, and this upper bound matches the lower bound we obtained, which is omega 1 over n. up to a constant factor, which means that in systems where ETH is a strong ETH is valid, then we completely solve the problem. We have an upper bound and lower bounds. The difference is only a constant. And I will now present the proof of this theorem, and it is given in the paper. So this is the last slide of this talk. I try to give a summary of the results. First, we have proposed a very natural definition of the convergence rate of the eigenstate expectation values in the thermodynamic limits. And with this definition in mind, we try to find the upper and the lower bounds of the finite size error. And the weak ETH, which is universally true in transition invariant systems, implies that we have an upper bound of order 1 over square root of n. And furthermore, we find that for certain local operators, in particular, if we choose the local operator to be a term in the Hamiltonian, then the finite size error can be identically 0. But we can show that there is a lower bound omega 1 over n for almost all operators. Almost all means that all but 0 set of local operators. And up to this stage, all the results holds for any transition invariant system in any spatial dimension, regardless of whether the model is integral or chaotic. And if we introduce a new assumption, which is generally expected to be true and which is numerically tested to be true in non-integral models or in chaotic models, then the assumption is strong ETH, then we can improve the upper bounds from 1 over square root of n to 1 over n, so that the upper bound matches the lower bound. So the final open problem here is that if we do not assume ETH, then whether it is possible to reduce or close the gap between our upper and lower bounds. And my conjecture here is that in any transition invariant systems, we always have a capital R, that is the finite size error is a theta of 1 over n for most operators, but this is, I cannot prove this at this moment. So this is the end of